All right, so this is a little bit of a different talk. So we have this library, which is quite big now. MATLib is, you've already been playing with it a little bit. But maybe at this point you're not so familiar with the kinds of things that appear in MATLib and the kinds of things that are not there. So if you think that there's some result that you want to use, how do you even know if it's in the library already or not? Because you don't want to go reproving things that are already there. So we're going to talk a lot about how to kind of get a feel for this. Now there's a bunch of different tools that we have. Okay? So let me point out to one which I think most people may not think of. And this is the undergrad list. Okay, so what we have here, let's see if I can scroll around successfully. So this is basically an undergraduate mathematics curriculum and links to things in that curriculum that already appear in MATLib. Now, we don't have everything that could be covered in undergraduate curriculum. If you look up here, there's a link for the things that are in the undergrad curriculum that are not yet in MATLib. And this list, we're not perfect about updating it, so sometimes something will make its way into MATLib and it doesn't get updated in this list immediately. But this is useful for giving you just a really high-level overview of a bunch of the things you might find. Okay? So you can look around, and the nice thing is that it's categorized based on familiar categories to mathematicians, right? So there's stuff about linear algebra, and we can see that, okay, we have the change of basis matrix, right? And we can link directly to that if we want, right? So this takes us directly to the change of basis matrix, and so it's saying something about basis 2 matrix and linear map 2 matrix times basis 2 matrix is another linear map 2 matrix, right? So whatever exactly those things are, let's not bother right now, but if we were looking for the change of basis matrix, this is telling us directly where it is, right? Now, I don't recommend using the undergraduate list so much in this way, unless there is some result that you think is very well known that should be directly in this list. It's more just to give you a feel for the kinds of things that you might find, right? So you can ask yourself like, oh, what kinds of things do we have about, complex analysis, as Vincent was talking about, or what kinds of things do we have about topology and normed vector spaces, right? So, for example, we have the normed space of bounded continuous functions, right? And we have actually kind of a lot of things about that, which is maybe not so obvious from this right here, but if you're wondering, does this thing exist, then this is a good place to look. Okay, but again, that's just sort of for an overview. Now, if you found something, you know that there's some declaration that exists and you found it. If you want to know a lot about it, the documentation is pretty helpful. So hopefully you've had a look at this already. But here's the MATLib documentation. Unfortunately, things are sort of cut off on the side here. But you could go through the files piece by piece, or you can use the search bar, right? Now the search bar, it's really not the most sophisticated search. It's just searching substrings. Now some things that you should know is that it's half case sensitive, okay? And what I mean by that is that if you use a capital, then it's telling you that, or you're telling it that you want it to be case sensitive for that capital letter, right? If you use a lowercase, it will match either capitals or lowercase letters. I know this is maybe a little bit of weird behavior, but if you're not sure what to search for, just search lowercase. Only search uppercase if you already know exactly part of the declaration you're using. But it's just matching substrings, so it's not very sophisticated. Okay? So, some other things that you can look at, if you're trying to find lemmas, one way is just guessing names, right? And guessing names can be an effective way to do it. We'll see an example in just a moment. But you can only guess the names if you know how things are supposed to be named already, right? And so this document has moved to the website. All right. Sorry about that. It gives, a lot of the conventions. Now the conventions are maybe pretty complicated, and I'm not asking you when you first submit your PR to MathLib that you would know all of the conventions. It's all right if you don't, and the people reviewing your PR can give you some help there. But it tells you a few things, like when you have a type, like a structure or a class, this is written in upper camel case. When you have things that are definitions, they're written in lower camel case. And so the upper camel case is something like one HOM, right? It starts with a capital letter and then uses a capital letter for each successive word. Then theorems get this snake case, all right? Where you have underscores in between words instead of just using capital letters. The one thing to note, though, is that when you have a theorem that refers to definitions, okay, it's snake case between the definitions. So one HOM is upper camel case, and we don't split it into one underscore HOM underscore injective. Okay, this is kind of a minor theorem, but it'll help you to read. It'll help you to read things in MathLib. So if you ever see like words squished together, that's like one object, right? Whereas if they're separated by underscores, they're different objects, or facts about different objects. Okay, so it's also just helpful if you know what a lot of the symbols are named, right? So a lot of them are pretty straightforward. If you have, conjunction, it's and. If it's a disjunction, it's or. If it's an if and only if, it's IFF, and so on and so forth. You can look through all these. I mean, a lot of them are maybe what you might expect, although I'll highlight a few that are a little bit weird. So, for example, if you have a binary union or intersection, that's just going to be union and inter. But if you have an indexed union or intersection, it's going to be I union or I inter, right? And there's this variant, which I won't get into right now. But then you can also take the intersection of an arbitrary collection of sets, and that would be S inter or S union, right? So S for set, I for index, right? So we, just knowing a little bit of these conventions can help you navigate the library, right? We also have that kind of thing for suprema and infima, right? The indexed suprema and the indexed infima. Okay. So I'm not going to go through this whole thing right now, but I just want to show you that if you're wondering how to name things or how to look up, like what should some kind of operator be called, you can look here and it'll probably show up. So you can use this to say like, okay, well what if I want to find a lemma that says something like for natural numbers, okay, n is less than or equal to, say, n plus 1, right? So the way I'm going to think about this is it's probably in the NAT namespace, right? But maybe not. Okay, and then I can do LE, sorry. Nope, I can't type. Failure. Underscore. Just tell me.
Just don't type it.
Just don't type it. Good point. Thank you. Okay, so we can say something like this: nat le add 1, and if you look, we get this result pretty quickly. Nat le add 1, if and only if. Right. So just knowing how things might be called can lead us to find them pretty quickly in the docs. Okay, and this gives us all of the type information about the theorem. But as I said before, the searching is kind of subpar. So we want to have other tools. Okay, so there's two other tools. I'm not going to talk about them right now so much because we're going to use them throughout the rest of the talk. One is Lugal, and Lugal provides a means of searching through MathLib, but in a way that's aware of lean syntax and expressions. and you can use like placeholders for variables if you don't know what the value is going to be and that kind of thing. Okay? The other one is Moogle, which is an AI solution, and this is useful for other tasks. All right, we'll get into exactly which one's which. Sort of the last two, one of them is if you're really, really stuck and you're not sure if something exists in Mathlib, but you think it might, you can just ask in Zulip. There's a whole stream called Is There Code for X? And you can ask things there, and people who know the library well will generally provide answers quickly. Okay? You can also just use the exact tactic. So I won't go into this right now because it's been discussed before, but the problem with exact is if the thing is not really in the library in exactly the way you want it, it might fail, right? So here, I'm trying to find that the square of the square root of a number is itself, but I've forgotten a hypothesis, and so exact fails to find it, right? Even though morally, we would hope that it would find something and be like, oh, you know, this almost works, but you forgot the hypothesis, right? So it's not going to be that smart. So we can get things with apply or exact, apply question mark or exact question mark. But again, it's a pretty stupid way. So let's say we want to find this result that the square root of x squared is itself just by using Lugal. So here we can enter an expression like this one. Okay. And it says when you oh shoot. How can I move this?
You can just move the window maybe.
Yeah. You can't move the window? Well, this is unfortunate.
Sorry.
It's okay. Maybe. Nope. Okay. Well, so when you search for square root and then to use a variable, you would use a question mark. So this is question mark x squared. Now you can follow along on all this. It's in the LFTCM repository. So if you can't see this for any reason, you can follow along in the document and click the links yourself. But when you search for square root and then question mark x squared, it says, wait, I didn't find anything. What are you talking about? And that's because it doesn't know that you mean the real square root, because there is no just sqrt in Mathlib. So it gives you some suggestions, and down here it says, oh, maybe you meant this. Maybe you meant real.square root, comma, something squared. So this is going to find all expressions. This is going to find all expressions that are that involve both real.square root and something squared, anything squared, right? So it finds a bunch, 108. That's 82 match the pattern. So that's a bunch, but we can maybe do better. Okay, so we could just look for real square root, but we can also look for this one. So this is going to, here we have that the goal, this is saying in the goal you want it to be, or in the conclusion you want real.square root of something squared is itself, right? And so when you search for this in Lugal, you find it right away, okay? And it's just that one lemma and bam, you're done, okay? Now that's still a pretty easy example. We could use Moogle to, just search in plain text the square of the square root of a real number is itself, okay? And when we search with Moogle, it doesn't return the theorem that we were looking for right away. It returns these other variants, right? And that's because it's not doing this type-driven search or the expression-driven search. Okay, but if we scroll down a little bit, then we get closer to it, and oh, I passed it. I'm sorry. That's n in real square root.
It went with x times x instead of x.
Aha. Yeah, so here we find things close to it, but we didn't quite find the right one, okay? So Moogle is good for like approximate searching, but it's not really good for exact searching like Lugal is, okay? It might be down there further in the list, I'm not sure. Okay, So that's just something to be aware of. And so yeah, you can find variance with this. Okay, but what if we want to find something that is just like a named theorem, like the first isomorphism theorem for groups, right? And maybe you have no idea what this should be named in MATLib. How do you even go about finding something like this? Well, when you have no idea what the names involved should be, I would recommend using Moogle first, just to give a sort of idea of what things might be named. So here you can just search the first isomorphism theorem for groups. Okay, and here we get something that's not really related, still not really related. Okay, still not getting there. And sometimes you have to go kind of far to find things that are relevant. Aha, and now we have something, quotient add group dot quotient cur equiv range dot proof 1 or something. Who knows? But it's, it says first isomorphism theorem, and this is maybe the way that Moogle found it, is because Moogle is aware of the docstrings of theorems, right? So if some phrase appears in the docstring, Moogle might be able to find it, whereas Lugal and just the doc search will not find it, okay? So at this point, you can kind of see maybe a little bit of the things that are involved. Okay, this is for add groups, but maybe there's a version that's named very closely for multiplicative groups. And we say, okay, well, probably quotient, cur, and equiv are things that might appear in the name, okay? But also, if we have, here's another one, okay? Quotient, cur, equiv, range. So this is G slash add monoid hom.cur phi, and then these other symbols that maybe we don't know right now. Okay, we could go to them in the docs and look around. So when we go to them, all of a sudden things become clickable. Like this, we can see what it is. What is this? This is an addiquiv, all right? So this is a type of like isomorphisms of additive groups, right? And we can also see other things like there's this slash, which is not a normal slash, it's a special Unicode slash, right? And we can copy this kind of stuff into VS Code if we want. So now let's see, all right, well, what if we wanted to find other stuff, right? What if we wanted to find this, maybe the multiplicative version, if we didn't find it already, using Lugal, right? Well, we would be saying, okay, I want the quotient of one group by some subgroup to be group isomorphic, and that's using this symbol here. That's using this symbol here, saying it's isomorphic as groups to some other group K. So that's just maybe more generic than we even need. But if we do it, oops, sorry. If we do it, then okay, we get a bunch of hits, right? And so maybe that's we do see the things we want here. Like this is maybe the theorem we want, but it wasn't like the only hit. So we can improve our search if we wanted to by actually including cur here, right? And if you do this search, then it's going to tell you, hey, I don't know what you mean by cur, right? Because there's a different kernel for for monoid homomorphisms and for other things as well. So you can say, okay, well we want the one for monoid homomorphisms. And we get this, right? And then it's maybe the first one we want, or maybe we want the version where the map is surjective, whatever, okay? So these kinds of tools can help lead you to the result pretty quickly. Now, another thing is, if you were thinking about we want this for groups, you might be kind of confused because it's talking about monoid homomorphisms, right? We didn't have anything about group homomorphisms just now. And the key thing is that we can use the same type for monoid homomorphisms as for group homomorphisms. And so in Lean, whenever we can do this, we generally do. We generalize some object and use it for multiple things, even if it's maybe means it's not named in the most convenient way, right? Okay. You could then apply these sorts of things to show that, say, if you take the integers and you take the natural homomorphism into the type of integers modulo n, which is z mod n, and you can find that with Moogle pretty easily. If you just like write the type of integers modulo n, then hopefully it would just tell you that's z mod, right? So you can take the natural quotient map in there, and then you should of course get that if you take that quotient map, that z mod by the kernel is isomorphic to z mod n, right? So here you can construct the homomorphism of additive groups. You could also get the one for rings, okay? And then you can use this result. You could use this result to actually prove that those things are isomorphic, okay? Just using some of the stuff we found. Now, the focus is not on being able to prove this result in this talk. It's mainly just about finding the results, so I'm not going to go through the proofs so much, okay? So here's a thing that should be pretty trivial, and so we want to figure out how to do it. But we're going to find out that it's maybe not as trivial as it sounds at first. So let's say you want to find the result that like if the number of vectors in some collection exceeds the dimension of a vector space, then the set is linearly dependent, right? So where are we going to find that? Now, if you're not familiar with MATLib, then you say, I have absolutely no idea where to look, okay? So one thing we can do is just search Moogle and say, if the number of vectors exceeds the dimension, the set is linearly independent, or linearly dependent, sorry. So if we do this, all right, we're going to look for results. We're just trying to get a feel for what kinds of declarations might be involved in a statement like this, right? So here we see, okay, this is something about dependence, but it doesn't say dependent anywhere. We see this is the definition of linearly independent. That's helpful. Okay, so it's just named the way we would expect. But what other things do we see? Do we see, the result that we just want? This one's maybe not terrible. Like, if I have a finite set, and this is linearly independent. Actually, this one's a little bit silly. I think actually we don't want this one so much. It's kind of a boring statement. But we can go down and we see that we're not finding a lot of stuff. In fact, I don't see anything that says the word dimension anywhere, right? And that's because in MATLib, we don't have the dimension of a vector space, at least not phrased as such, right? If we scroll down to this one, okay, no, not that one. The next one, we see it saying something about fin rank. So finite dimensional dot fin rank, okay? So that's another declaration which we might want to know about. But it seems to apply only to finite dimensional things. So maybe we are a little bit skeptical, especially if we want this for infinite dimensional vector spaces, right? So maybe those two things are handy, but maybe not. Okay, and then we see, okay, there's this other notion of rank. There's this module.rank, okay? So now we have two different kinds of rank. Module.rank, which should be the dimension of module, but it's a cardinal, okay? I mean, we can find that out by going and looking at the docs, right? Or we have this finite dimensional version of the rank, which is the fin rank, okay? So, if you look around, at least the first time, or the time I did this before, I found some results on Moogle. And the closest result was like this exists linear independent cons of LT rank, or linear independent if and only if card equal fin rank span. So let's just take this and search it in the docs. Just to see what it is. Okay. So this says a set is linearly independent. Here B is a function from I to V, okay? So I is some type. If and only if the fin_type.card, that sounds like the cardinality of I, is the set.finrank, which is different from the other thing we saw a minute ago, which was finite dimensional.finrank, right, of K of the set.range of B. Okay, so this is maybe okay, but it doesn't appear to be the nicest possible statement. It's a statement though, right? So what if we wanted to do some more searching like this? So one thing to do would be to collect like the declarations that we've seen. So linear independent, module rank, finite dimensional.finrank, and this other one that seemed as close as possible, right? So I'll show you that if you try to apply that lemma we just found, you can do it, okay? And you can get this theorem, which says that if the module rank is less than the cardinality of this index set, then the collection is not linearly independent. Now, this is a kind of complicated proof, right? It's many more lines than you might have expected. You would have hoped that this can be done in like 1 or 2 lines or something. It's a very basic result. Okay, so this kind of thing, if you're going through a proof and it's really hard like this, it often means you're not quite getting the phrasing right. Okay? So you want to look for other phrasings. So let's just look for this in Lugal. Okay? And we're just going to search for things involving linear independent and module rank. Okay? And we get, I know it's maybe a little bit hard to read, but this first result is actually, the first and second result, I think they're basically the same thing. It says that if you have some collection of vectors V and they're linearly independent, then the cardinality, or the cardinal corresponding to the type of the index set, is less than or equal to the module rank. So if you notice, this is basically the contrapositive of the result we want, right? And so this is very close to a theorem that we're looking for. And note that when we started this, we had no idea what anything was called, right? But we used Moogle to figure out what things were called. And then we used Lugal to kind of refine our search in a better way, using only those declarations that we know would appear, okay? So that's kind of a helpful thing. And so with this, you can actually get a pretty quick fact, or a pretty quick proof, right? So all I did here is I just basically restated the lemma, but I restated it in the contrapositive version that I wanted, okay? And then I just said, okay, take the contrapositive, do some simplification, and then I used exact question mark, and exact told me, hey, I should put that in, which is exactly the declaration that I just found a moment ago using Lugal, okay? So yeah, once we know what things are called, then we can perform better searches and hopefully find the thing we want better. Now, the other thing to note is that actually, what if we really were working with finite dimensional spaces? Because although I'm not going to talk about it at all, using cardinals in MATLib is kind of annoying. I won't talk about why because it's not the purpose of this talk, but just suffice it to say it's sometimes annoying. So we might actually want to work with this fin rank instead, because if we look at the docs, the fin rank is actually just a natural number. Okay? So maybe we want to work with that instead because it's easier. And there is this related declaration which we could find if we use Lugal again, okay? Or even searching MATLib docs, we can find this result. Linear independent.finTypeCard LE finrank, okay? And so this is the same kind of result as this one, except it's phrased with slightly different things involved, right? So instead of the module rank, we use the finite dimensional.finrank, okay? And then we can get the same kind of result. So now if we look at this lemma below, all right, if we have a finite collection of vectors, that's this fin type I and then the function b from I to m, if the finite dimensional fin rank of the module m is less than the cardinality of I, then the collection B is not linearly independent. And again, the proof is very similar to the one we had before. It's just contraposition, and then you simplify and use the exact statement from MATLAB that you want. By the way, I'm pretty sure that the exact statement we're going for here does not actually appear in MATLAB explicitly. And I think this is because we have very, very few things that are phrased in terms of where the conclusion is not linearly independent. Okay? So, I'm not sure exactly why that is. Maybe we should have these results. I'm not totally sure. But they're at least very easy to get once you know what things should be involved. Okay? And so this is even a different, this is like a really explicit example that we can do with this. Okay, if you have a natural number and you have a finite set of vectors from in n-dimensional space, and the cardinality of that finite set is greater than n, then that collection of vectors is not linearly independent. Okay? And so we can just prove it using the other stuff we've done here. Okay? Or if you want like a really explicit example, you can do this too using the result we proved above. Here I've got 3 vectors in R2, and we're concluding that they're not linearly independent. Okay, so that's kind of a long example, but I think it highlights a lot of the things that you can do and a lot of the workflow that you might use. Okay, so there's a lot of times where if you use Moogle, it can just win straight out of the gate. So like let's say we wanted to know the transition matrix between orthonormal bases is unitary. I plugged these exact phrases into Moogle and got these declarations out as the first hit. And they are exactly the correct declaration to be looking for. Okay? So, and this works for a lot of different things, right? The category of modules is abelian. Bam, done. Right? The open mapping theorem in functional analysis. Continuous linear map dot is open map. Right? Some of these maybe we could have guessed. But how about the Hahn-Banach separation theorem? Right? This was the first result. But if you go down just a little bit, you have things like convex cone dot hyperplane separation of non-empty of is closed of mem, right? But just to show you, like the declaration of geometric Hahn-Banach open, right? It's saying, okay, if you have a convex set and it's open, and T is another convex set, and they're disjoint, then you can get an F. And it doesn't say here what F is, so that's maybe something that is a little downside of the hover. Sometimes the hover doesn't give you as much information as you might like. Okay? So if we're lucky, no, we're not lucky. Okay, so that doesn't work. I was hoping to hover over the F and get more information, but it's not the case. So maybe one thing you could do is you could go to the docs. But actually, the docs might have this problem too. Another thing you can do is if you right-click, you can click Go to Definition, right? And so Go to Definition, this tells you, oh, okay, that F, whoops, sorry. That F is a linear map, a continuous linear map. And if you're not sure, like if you're not familiar with that notation, you can hover over it and it will tell you, please. Maybe it won't. Yeah, continuous linear maps. There we go. You got to hover over the right thing sometimes. But this tells you, okay, this is a continuous linear map, continuous linear functional even, right? Okay. So these are the kinds of things you can do. So Moogle, sometimes it gives us a lot garbage, but sometimes it's on the money right out of the gate. And additionally, even when it gives us garbage, or mostly garbage, sometimes we can sift through it to find things that are relevant, right? And then we can do other searching from there. And again, I recommend that when you have absolutely no idea what things should be called. If you already know what things should be called or what they're called in MATLAB, then maybe Loogle is the first thing you would go to. Okay? So I had asked some of the organizers last week for some challenge problems. Some things that's like, what are things that you think might be hard to find in MATLAB? And I'll try to go find them. Okay? So one of them was Benet's formula for the nth Fibonacci number. Okay? So if you try to use Moogle for nth Fibonacci number or Benet's formula, then I think it might do better today, but I think that's because someone added a doc string somewhere. So let's just try Benet's formula. Okay, yeah, so it's giving us something Bilin. I think this is what I got before. Maybe, okay, and there's also things where it can be pretty sensitive, so I didn't put an apostrophe. So, no, it's still giving us pretty much garbage. Yeah, okay. So sometimes you just really don't have luck. But in this case, you might just search for something simpler, like how about Fibonacci number? Right? You search for Fibonacci number, and you say, okay, fibrec, that doesn't look quite right. But then you see, oh, nat.fib right here. Okay, so it should be something involving nat.fib, right? And if you know Benet's formula, then you know that it should probably involve a square root of 5 somewhere. So searching Lugal is going to do much better. Okay, so we just search Lugal for nat.fib and real.square root, and we get exactly Benet's formula for the nth Fibonacci number. Yes?
If you do a plain text search in MATLAB for Benet, you get it. It's like there's 2 results and one is Benet's formula. So,
But you mean in the docs?
like a plain text search.
Okay, yes.
Right.
Yeah, okay, yeah. You can grep through MATLAB, but let's
Let's open it in the doc. I don't know if it's rated B. If Binet is
Yeah, that's why I said you go to GitHub and you press search, like the search button.
sorry, what was this?
yeah, but for example, in VS Code, if you are working on your project, the search button doesn't.
Okay, so it does say Benet's formula. It's possible that Moogle hasn't been updated on the latest MATLAB. I think this doc string was added pretty recently. Okay, but yes, you can just grep through MATLAB, but I'm not going to assume that people know how to grep here. GitHub search, okay. All right, well, yes, there may be other ways. Okay, so another one was the Weierstrass M-test, right? And if you search for Weierstrass M-test, then you again get garbage on Moogle, right? Just things that are totally unrelated about Witt vectors and, you know, who knows why it's doing this exactly. Weierstrass curves, okay, still not related. All right, and if you keep going, I think it doesn't even show up. Okay? So, but if you know what the statement of the Weierstrass M-test is, we should say, okay, there's maybe some keywords, like a series converges. Again, this is one of those situations where we don't know what any of the declarations in MATLAB are called, right? So you might try something like series converges. Okay. The second result is this summable dot tends to cofinite 0, which you're like, okay, that's maybe a little bit weird, but summable seems like it might be related. So now we know that there's this declaration called summable in MATLAB, and maybe that's a useful one. Okay, and we can keep going down, but we don't find a lot that's relevant. Okay, so you still want to search for what other things? Okay, well, the Weierstrass M-test is about like uniform convergence, right? So maybe we can search for, maybe we can search for that. Maybe I didn't pay enough attention to the series converges one. Sorry, if we look around here at series converges, we see something about has some, tends to of subsequence 0. All right, so we're not seeing a lot, but we might go check out what this summable thing is in MATLAB. Okay. Nope, fail. Try that again. Okay, and if you look at summable, it means that f has some infinite sum. Use tsum to get the value. Okay, so now we see that there's this other thing called tsum, all right? And if the sum, it's the sum if the sum exists, or it's 0 otherwise, okay? So now we know a few things that are rolling around here. We've got summable, we've got tsum. These are related to infinite sums. That's good. But we still don't know too much. But notice that we haven't searched for our other keywords that we thought about when we were looking at the Weierstrass M-test. So you might consider looking at searching Moogle for uniform convergence. Okay? So, okay, uniform convergence, term something, I don't know what that is. You say, and they say, okay, filter.tends to conger uniformity. You know, maybe I still don't understand what the uniformity is or anything like that. So we're just looking around for things to help us. And then we see some things like tends to uniformly on filter. Maybe you're not comfortable with filters yet because Oliver hasn't talked about it. But okay, this is something that looks pretty promising. This is something about tends to uniformly on. Uniform convergence on a singleton is equivalent to regular convergence. Okay, so this is somehow about uniform convergence. So, you know, you can go to the MATLib docs and you can say, all right, well, tends to uniformly on. And you can search for that declaration. Okay, it says a sequence of functions fn converges uniformly on a set S to a limiting function f with respect to the filter p. Still, maybe I don't know what filters are, but who cares? It seems to be about uniform convergence. If for any entourage, whatever that is, one has p eventually this. Okay, so you know, maybe you don't understand some words, but it definitely seems like this is about uniform convergence. All right? And so now we have a few things that we can maybe try to Loogle with. Okay, so if we go back to this, we were taking notes, and we said, okay, some things that were relevant were summable, maybe filter.tends to, tsum, maybe we didn't find tsum def, but, and then for uniform convergence, we've got this tends to uniformly on. So let's just, you know, use Loogle and say, see how lucky we can get. What if we say something like summable and something that involves summable and tends to uniformly on? Okay. All right. Tends to uniformly on tsum nat. All right. And actually, these two results are exactly the Weierstrass M-test. If you look at it for long enough, then you'll see it. Okay. But I know the statement's kind of long. Okay, but just to point out, we knew absolutely nothing going into that, right? Into that exercise. We didn't know what any of the things should be called. We found out what they were called, and then we used Loogle to narrow the search a lot. Okay? So, there's other ones on here, but in light of time, I'm going to skip a few. You're welcome to read through them. It should, this document should give you a pretty full description of what's going on, and you can play with it yourself and walk through the examples. Okay, so let me just say this one, because this is a pretty surprising one. So if you're familiar with Dedekind domains, or even if you're not, there's multiple definitions. Okay, and so one of them is it's an integral domain that's Noetherian, integrally closed, and has curl dimension at most 1. This is the definition of is Dedekind domain in MATLib. Okay, but there's this other equivalent definition, which is every non-zero proper ideal factors in the product of prime ideals. Okay, so what if you do, like, you know, MATLib obviously knows some things about is Dedekind domains. If you just start searching the docs, you'll find that things exist. But where is this result going to be that, that 1 implies 2, right? Where is that going to appear? That a Dedekind domain satisfies property 2. And the problem is, if you go searching, you're really not going to find it. It is in MATLib, but if you go searching the docs, it's not going to appear. And this is why it's important to kind of understand how we phrase things a little bit. Okay? So the key thing to note is that if you have a ring, right, the ideals also form a ring. Okay? And if you look at this second statement, okay, or sorry, not a ring, but a semi-ring. Okay? In particular, they have a monoid structure. And if you look at this statement, it's some statement about factorization, right, of into prime ideals. Okay? So that's actually, the fact is that in a Dedekind domain, the space of ideals has unique factorization, or the set of ideals has unique factorization. So it turns out that if we start looking for unique factorization, okay, well, maybe there is not the best place. So, we could search for unique factorization. Okay, and we get this thing that says unique factorization monoid. Okay? So if I go to unique factorization monoid here, just by clicking around, okay, so this is exactly UFDs except for monoids, right? Because we only ever refer to the monoid structure. And you see this is a class. Now, Floris is going to talk about classes and instances tomorrow, so I won't go too much into it. But sometimes Lean can know things that are sort of hidden in the background. And so it turns out that under these hypotheses, so R is just a Dedekind domain, we can ask Lean if it knows that the ideals of R form a unique factorization monoid. And the way we ask it this is we say, okay, unique factorization monoid, ideals of R, right? And we say synth here. And synth is asking Lean, okay, it only applies to things that are classes, but it says, do you know that this thing is a member of that class? In other words, do you know that it has that property? And Lean returns and says, yep, the output of this, in your info view, if you look at it, it'll show this. And that's the declaration that tells you that 1 implies 2 above. Okay? So sometimes things can be kind of hidden like this. And this one's just a little bit tricky. Probably, I would have had trouble getting it if Johan didn't tell me what it was, the answer was up front. Okay? Okay, so just another thing, how to phrase things in MATLib. I can't go over everything, but just to show you that maybe the words that you're used to using don't appear exactly that way in MATLib. So for example, if you want to say that E is a Banach space over some field K, right, how do you say that? Well, we don't have the word Banach space. Okay? What we have is this really more complicated statement. I'm sorry, I got cut off at the end. But E is a normed ADCOM group. K is a normed field. E is a normed space over K. And then to get the Banach property, E is complete. Right? So you kind of often say it as this collection of conditions, which are sort of pasted together. This should be covered, I think, more in Floris's talk tomorrow about what these square brackets do and sort of what they mean and how things are structured. Okay. If you want to say things like other common things, like what if you want to say that something is finite, like a set's finite, right? Well, there's unfortunately a number of ways to do this, and they are all related, but you use them in slightly different contexts. And this is probably a pain point for new users, but I'll give you just a brief overview about when you should use what. If you have a type, and you want to say that's a finite type, there's actually 2 ways to do it. You could either say that it's a fin type, and this is sort of constructive, or you could say finite x, and finite x would be the statement that it's like a propositional version of the statement, a non-constructive version of the statement that x is a finite type. However, for sets, okay, if I have a set, there's a few ways to say that's finite. Either I can say it's a fin set, which is like another constructive type version of being a finite set, or I can say set.finite s. Okay, so there's multiple ways to phrase this kind of thing. Okay, if you want to say that there's a bijection, there are multiple ways to say that too. You can either just say it as a proposition, like some function is bijective, function.bijective, or you can build an equiv. So an equiv contains the formula for the inverse of the function as well. So it's providing a function and its inverse and a proof that they're inverses of each other. This is often the nicer way to go, okay? Because then you sometimes want to access that inverse function. And if you use function dot bijective, it's maybe not so nice to work with. So a lot of times the way we're giving bijections in MATLib is actually by giving equivs, or sometimes equivs with extra structure. So like a mul equiv would be a group isomorphism that contains the data for the inverse isomorphism as well. Okay? All right. So here's an interesting one. How do you say the set of natural numbers such that 0 is less than or equal to n is all of n? Right? You might be tempted to just say, put an equal sign in between those two things. Okay? But unfortunately, that's not going to be valid in Lean, and it will complain at you immediately. It will complain saying, you know, you can't say that these two things are equal because they don't have the right type. Okay? So, because on the left-hand side, you have a set in n, and on the right-hand side, you have a type. So if you want to refer to all the natural numbers as a set, this would be set.univ. Okay? So this would be the way to actually phrase that in Lean. Okay. Yeah.
Is this just some kind of, you forget the extra structure on n, or is it like the underlying set, or?
It's sort of the underlying set. This is sort of a bit of technicality that in Lean it's not actually based on set theory, it's based on type theory. So things are at a fundamental level types, but we also want to refer to subsets of them and so forth. So there's the type. This is maybe a stupid thing for me to say in my talk, but there's the type set, and a set is the collection of elements of some type, but this is the type of sets. So set capital N, or set math BB n, is the type of subsets of the natural numbers. So if you took S colon set capital N, S would be a subset of the natural numbers. Okay? And just referring to the set of all natural numbers is different than referring to the type of natural numbers. And that's sort of the thing going on here. So yeah, it would be set.univ.
What does it do?
Oh, it's basically like writing curly brace x is an element of n, vertical bar true, right? It's effectively that way to write. It is literally that thing, yes. So, okay. Okay, so another thing that's maybe a bit slightly unfamiliar is this idea of induction principles. And I have 5 minutes, right? Okay, induction principles. So normally in mathematics, when you are going to do something by induction, you say, okay, I'm going to take the dimension of my vector space and I'm going to do induction on the dimension, right? But one thing that you almost never say is, I've got a compact set, I'm going to do induction on that compact set, right? That's a very weird thing to say mathematically, but in Lean we're going to say that kind of thing much more frequently. And we have all of these induction principles for various kinds of things, right? So if, some of them are pretty familiar. One example of something that's pretty familiar is sub-semi-ring closure induction. So if you take a semi-ring and you take a set in that semi-ring, you can take the closure of that set as a sub-semi-ring, right? And all you're doing basically is you're just throwing in 1 and 0 and addition and multiplication along with your elements of your set and taking the smallest sub-semi-ring that contains all those things, right? That's closed under all those operations. So if you wanted to say that something was true for the sub-semi-ring closure, you might show that that property holds for all elements in your set, and that property is closed under those operations, right? And that would be sub-semi-ring dot closure induction prime. Ignore the prime, it's not that important. And so then you have, if you look at this proof, I'm doing induction on the fact that x is in the sub-semi-ring closure of the rational number 5. And I have if you notice, I do this induction with, and if you don't know what the things come after the with, there is a, it's not here because, hold on. Nope. Okay, it's not here because it's filled in already. Nope, okay. When you type with, if you have nothing after it, there will be a little light bulb that pops up on the left. Okay, and you can click that light bulb and say, generate the skeleton of the inductive structure. And it'll fill in all of these pieces for you, like the mem and the arrows and the 0 and the arrow, 1 arrow, add arrow, etc. Okay, so it'll fill all these things in for you. All right, and then you just have to go through and prove each of those facts. Right? So another thing that might come up in mathematics that you would do frequently is say, I want to do induction on the cardinality of some finite set. Okay? So I want to prove something's true for all finite sets, and so I want to do induction on the cardinality of that finite set. In Lean, you could do that, but it's kind of trickier because you have to take your finite set, then you have to like find its cardinality, and then you have to like clear that variable and do induction on that variable. It's kind of messy. Instead, you can just use the induction principle for finite sets. So here I have S a set, and the fact that it's finite, and there's this result, this theorem in the library called set.finite.induction on. And that's the lemma that I'm applying here. And then in order to apply that theorem, I couldn't quite use the induction tactic because something was broken here, but I have a few cases that I have to do. I have to do the case where it's the empty set, and then I have to do the case where I have a finite set for which the property holds, and I add some other element to the finite set. We can look at this result real quick if we want. So set.finite.induction on. Okay? So, right. This says if you know that something's true for the empty set, and for any set, finite set for which it's true, and any element not in the set, then it holds when you add that element to the finite set, right? And so here I never have to mention cardinality, which makes my life slightly simpler in Lean. Okay? So, yeah, just some things that you would do differently. Just a few more things and we'll be done. You can use this command help. And I'm not saying it's the most useful thing, but it can provide some information. So we'll see how it is useful or not. Can I? Yes. So if I look at help tactic, this is going to give me help about the tactic ring. And you know, here this gives me a bunch of information, including examples of how to use ring. Okay, but sometimes it's not the most. Sometimes stuff is not as useful. For Peel, it gives me some decent information as well about what the tactic Peel does. Ext gives you some information, right? But if you ask it for other things, sometimes it's pretty sparse. If you ask it, what does the attribute simps do? Automatically derive lemmas specifying the projections of this declaration, the simps attribute, right? So this is a doc string that we should definitely update at some point because that's just terrible. The information is contained somewhere else and it doesn't appear in this, so we need to move that information here. So sometimes things are just bad and not helpful. Help attribute ext marks a theorem as an extensionality theorem, right? Like, it's not giving you a ton of information. So sometimes it's going to be helpful to you, and sometimes it's not. We're basically done. There's an example at the end here which shows you that sometimes things that are simple are actually missing. And this is a real world example from me from a few weeks ago where I went looking for like the intersection of a finite open interval and an infinite open ray, and there was nothing about the fact that this was a finite open interval again, right? And so you can search with Moogle and Loogle, and it's just nothing comes up. And I even asked on Zulip in the is there code for Xstream, I linked to that thread here, and it's like, yeah, it's just not there. So, you know, you need to add it, right? Okay, so thanks, I appreciate it.
Are there any questions?
Yeah, just a simple question. Why they're like called like this? I mean, Lugul and Mugul. Like what's the?
Well, I think the play is on Google.
Yeah.
Lugal is for lean Google, I
Okay.
assume. Moogle, I'm not actually sure. Do we know?
I don't know.
Okay, we don't know. The creator decided it should be called Moogle. Maybe because M comes after L, I don't know. Maybe that, yes, okay.
Some other question? Yeah.
So it's just to complement the previous answer. I think it also comes from a Hugel, which did the pun for Haskell before.
Yes, definitely. Agreed.
Any other question? No. So let's thank Gerard again.